In this video, we're going to continue discussing the interpretations of the Gibbs free energy. So previously we talked about when a reaction was going to be spontaneous. That is when our free energy, our delta G of the reaction, is negative. What situations will that be the case? Well, for an endothermic reaction with an increase in entropy, it's spontaneous at higher temps. For an exothermic reaction with a decrease in entropy, it's spontaneous at lower temps. For an endothermic reaction that reduces the entropy, this is never spontaneous at any temp. You're trying to corral particles and energy back into one position in both these cases, which is fundamentally against the idea of spreading energy out throughout a system. And finally, an exothermic reaction that increases entropy is spontaneous at any temp. You are spreading the energy out, increasing the entropy, distributing that energy throughout more states. This is favorable and spontaneous at any temp. Since temperature can affect half of these conditions, we can actually identify at what temp that will occur. What will be the temperature where the spontaneity will flip between spontaneous and non-spontaneous. Let's look at our starting example here. My delta G is going to equal my delta H minus T delta S. Let's just assign some numbers. Let's say I have 10 for my delta H. I'm going to subtract from that temperature times 1. So as my temp increases, I will subtract a larger and larger amount. But at first, if temp is 1 or 2 or 3, I'm positive. I'm getting 10 or 9 or 8 or 7 for my delta G. But eventually, as we get to 8 and 9 and 10, this becomes 2 and 1 and 0. And then when our temperature gets enough, our delta G will become negative. Right here, where delta G was 0, that is our transition point. What temp we are at that point, that is going to be the temperature where any hotter or any colder will swap between spontaneous and non-spontaneous. So if 0 is equal to our delta H minus T delta S at the transition point for spontaneity, then we can rework this to say that the temperature times the change in entropy is going to be equal to the change in enthalpy. We'll add T delta S to both sides. We get this equation, divide by delta S. The temperature is going to equal the delta H of the reaction over the delta S. Make sure the units are the same, joules instead of kilojoules and joules. But this information allows us to actually identify at what temperature a reaction will change between spontaneous and non-spontaneous. So this is one thing that delta G can help us find. However, what is delta G generally considered? What is the Gibbs energy? In general, we think of the Gibbs energy as the maximum work a chemical change can do. As the energy is distributed, it's possible we can harness that flow of energy. But there's a maximum amount that we can harness. Some of it is just tied up in molecular motions that are not something we can make use of. When we say harness work, think you've got a bucket of water, and you've got a hill and a flow, and you've got a wheel. So some kind of water wheel. It's got planks that the water can hit. Now in theory, if you design the slope right, you can have that water pour over, hit the wheel, flow down, and then go on its way, and it will drive the wheel. The wheel will turn. You're exploiting gravity pulling the water down to twist that wheel on its way. Now you could still have that happen if you had a little hole and the water just drained here and then flowed. The water still ends up where it's going to go when gravity pulls it down, but your wheel didn't turn at all. In one of these cases, we were able to harness the flow of the water to perform some useful work, turning that wheel so that it can spin some gears, grind some grain or whatever it was used for. Maybe cut some wood. Old wood mills work this way a little bit. However, if you don't have that water flow correctly over the wheel, it still reached the bottom. All the potential work it could have done has been used up. It's gone. Once on the bottom, the wheel won't do anything anymore. Even if you do get it to hit the wheel, it's possible some splashes over and some flows through. If you just open the chute, you might pour water out too fast, and a lot of the water will ricochet off the top, fall down, and not have successfully turned the wheel as much. Some of the potential work got used, but not all of it. In any real system that we can design, there's always some wasted effort. Some of the potential didn't get used for the thing we want. So while delta G does tell us the max that could happen, the reality is we will never obtain that. We'll obtain some lesser amount. Well, that's when delta G is negative. If delta G is positive, then this is minimum work needed to be done to the system. Go back to our example, I guess, right there with the water wheel and everything. If I've got a bunch of water at the bottom and I want to put it up into the container, well, I'd have to have some kind of pump system and I'd have to push it up. You could imagine a person holding a bucket, picking up a little bit of water at a time and carrying it up some stairs to throw it in to the large container. Now, moving that water physically up takes a certain amount of energy. But the person's also walking themselves, sloshing side to sides. How much energy is just used to maintain the bucket? If they set it down for a minute, they lose a little height, lose a little potential, then they have to pick it back up again. There's just waste. You will never, ever be able to get it up into that container using the minimum amount of necessary energy. So the positive delta G tells you what the minimum work would be needed to push your system back to its starting point. But the reality is, because of the inefficiencies in anything we can design, it's always going to take more work than that to go back. So when a reaction first occurs and gives away some amount of energy, we can harness a little of that. If we tried to use the water wheel to power this system, so you would start with water up above, maybe have a little pump down here that would pull the water back up. Well, your water would flow. You'd harness some of the energy, use that energy to push some of the water back up. But over time, due to the inefficiencies, you just end up with less and less going back up until, in the end, you just ended up with water down below. Every step of the way, you're losing some energy to inefficiency. Delta G is merely telling us the max possible. It's up to us to engineer something that can harness as much of that as possible. When we think of car engines and the like, they're often only 15-ish% at best of all the energy of your gasoline burning, giving off heat. About 85% is just lost. It's not used to drive the piston. The piston moves really fast and then it's thrown back down by the motion. It had kinetic energy that could have continued going up. But in order to cycle fast enough, we waste a lot of it by shoving it back down too early. Car engines are notoriously inefficient. Electrical systems are far more efficient, and some of them get up to about 80 to 85% efficient in realistic usage. So what is delta G really describing for us? Well, it's the amount of entropy for the universe. But as that energy leaves your system, as your reaction or chemical change progress, it's possible to harness the flow of that energy for work.